Thanks, everyone. So I'm going to present our paper, Interacting with Other Agents Without a priori Knowledge, a Radical Interactionism architecture developing from the ground up the ability to infer motivation and predict behavior. This work is based on a Radical Interactionism framework that considers the exchange between agent and environment only under the form of sensorimotor chain that we call interaction. It also proposes a kind of intrinsic motivation that is based on the satisfaction value associated with the interaction. We also base work on the previously developed architecture, the space memory architecture, that construct data structure to represent the affordance affording the interactions only based on the previously enacted interaction, and construct a data structure, the emergent space memory, that generate and maintain a local egocentric context of affordance around the agent. So now our goal is to study the emergence of collaborative or competitive behavior in multi-agent context. To do so, a radical interactionist agent must be able to integrate other agents in this model of the environment and be able to generate efficient behavior to interact with them. Previously, we defined 5 processing steps that must be implemented to allow an artificial AI agent to interact with other agents, that are defining, recognizing, and localizing mobile entities, being able to observe the behavior of the mobile entity, inferring the behavioral preferences of the entity, predicting the future move, and then finally generate behavior allowing to interact with them. So this presentation will concern only the 2 last parts. So to test our model, we develop an environment populated with multiple elements. We have the agent represented with a gray shark here. We have mobile fish that can move in 4 directions or remain immobile. We have alga, red alga, and green walls. The fish are driven by a hard-coded version of the model, the reactive model of the agent, making the fish moving toward, strongly attracted by alga that they eat, and slightly repulsed by walls that they avoid. The agent itself is equipped with 6 primary interactions that consist in moving a step forward, bumping in a wall, in a solid object, eating, sliding over a soft object, turning left and right. It is also equipped with a visual system that can see 3 colors at different positions, initially unknown, while enacting a primary interaction, which define 2,000 secondary visual interactions. As an external observer, we can organize this unlabeled set of interactions like this, with the primary interaction here, and each group represents a subset of visual interaction that are organized that are gathered by a group that are related to the same primary interaction and matching their ground truth color and position. The signature implemented with a formal neuron, so by organizing the weight in the same way, we can see how the agent define its affordance for each interaction. For example, here we have the two interactions related to static elements, bump and slide, and we can see that they organize, that the agent clearly identify that they are related to the presence, respectively, of a green object and a red object in front of it, which is consistent with the environment property. The visual interactions that are also interaction also have their signature, and we can see that this signature encodes the movement property of the related primary interaction. So it is possible to use this signature to project the signature of an interaction in space and detect distant affordance. We have here the example of interaction related to dynamic elements. I only represent 2 rows over the 5, but we can see here the context related to static elements that are detected with high probability, while elements related to dynamic elements are detected with a lower probability. The front position, which means no movement of the fish, has a slightly higher probability because the prey can be stuck by a wall. So thanks to this signature, it is possible to detect distant affordance. We have here an example. Each circle represents a position from which represent a sequence where the distant affordance is detected. So the position from which it is possible to interact. We have here the static elements that are detected. And we also have that the static elements are sent into the space memory. And we have the dynamic elements that are detected through multiple sequences, as the element can be interacted through multiple positions. Then the idea is to simulate this sequence in the space memory to get the context from the point of view of the mobile entity, which made possible to detect the distance of the other static affordance from the mobile entity. Then, by following the mobile entity through multiple consecutive steps, it is possible to detect variation in distance and first to infer the behavioral preferences of the mobile entity. Our previous work here shows that this can be done quite accurately. So now we can detect a mobile entity and infer and know their behavioral preferences. The agent can start to predict their next moves. Yes. So the agent projects its own motivation, its own decisional model that consists in moving toward affording interaction with high satisfaction value. So it depends on the inferred satisfaction value for the mobile entity and the distance of the other surrounding affordance. And we define a utility for each of the positions. And the agent keeps the position with the higher utility value. In this case, it is this one, which corresponds to a position here, nearly, mainly because of the presence of this wall that makes the agent prefer this position over this one. So we have the next position of the mobile entity as a sequence of interaction. But this is not sufficient to continue. We have to convert back this sequence as an observation in the interactional context, so as an enacted interaction. So we propose to project the signature of the interaction here of it. But as we know the object is present, we don't have to project the whole context. We just project the higher weight of the most probable context. So projecting a signature consists in back moving the sequence from the end to the beginning. And we start with the most probable context related to move forward, get the highest weight, which designates a specific interaction, here visual interaction of seeing blue. We get the signature of this interaction, get the higher context, higher weight, and so on until we back move the whole interaction. Then we have here an interaction that we can use, that is the one that is the most likely to represent the new position of the prey. So we can replace this interaction in the interactional context, so how the agent perceives its environment. And we have the next position. So now we have an interactional context. We can perform the detection and prediction, and thus recursively. So we have a plausible trajectory of the mobile entity. Here, for example, the agent has learned, has detected that this fish will move toward this alga. The trajectory may differ from the real trajectory because the agent has different sensorimotor possibilities, but we have the movement, the main movement of the mobile entity. An interesting point of this mechanism is that when detecting recursively the position through a sequence of interaction, the agent may discover sequences that have the same length than the simulation step, which means that this sequence will allow to intercept the mobile entity. This is why we call them the interception sequence. And the agent may use this sequence to define the position that it will consider in its decisional system. So the position is not, you not use the position of the agent, the mobile entity, but you define the position as a possible rendezvous with the entity. So I show you I show you an example of behavior here without the prediction mechanism. So the agent will only follow the prey by using the most probable sequence. But as they move at the same speed, the agent will not catch the fish until it stops. With the mechanism, when we use the mechanism, the agent detects interception sequence and tries to start to follow them. And you can see, for example, at this moment here, that the agent cannot see the prey, but can still use the interception sequence as a kind of memory to continue tracking and catch the prey before it reaches the alga. So by adding these two mechanisms, we completed our extended model for the space memory to integrate mobile entities. So with this model, we demonstrate that it is possible without any a priori knowledge about the environment to define, detect, and localize mobile entity, estimate the behavioral preferences, intercept and interact to generate the behavior allowing to interact with them. We have also, for the first time, the emergence of allocentric reference because the position of the mobile entity is defined through the context of static affordance. And in the future work, we will design more complex the exploitation mechanism. We'll try to integrate the agent itself in the model of the environment. We'll also study the emergence of collaborative behavior, such as collaborative hunting of large prey, and try to see it is possible to infer the presence of an affordance through the behavior of other agents. Thank you for your attention.
Thank you, Simon. Is there any question? One over there.
Yeah.
Hello, thank you for a nice talk. Do you think you can extend this to the continuous world?
Yes.
To the continuous world, because there's a discrete world.
Yes, sorry.
It's nice work, but can you extend this to the continuous world? Like most of us, we work with robots.
Yes, it's the topic of my second presentation.
Of?
In the second presentation, I will show how to use this model in a continuous environment.
Oh, okay. And it also depends on the horizon, I guess. Huh? You have the horizon, the view that you can see, so the amount of pixels you can see, so you don't see the whole world in your
exactly.
setup.
The agent is
and it also plays a role.
Sorry. This one, the visual field is limited in distance, but we should use logarithmic the distance to map the whole environment while losing the distance information while the perception become when you increase the distance. That is possible. Here we only use a grid splitting of the environment to make the observation more simple to analyze. But we also tested at the beginning with polar coordinate. It also works, but it's hard to analyze.
Is there any other question? Otherwise, I have one which is partially related to this. If I properly understood, you only tested in this scenario, right?
Yeah.
Have you tried to change the topology of scenario, and in that case, so like the same agent changes scenario and the capability to generalize eventually over other typology of, if you change the way agents are represented, preys are represented and so on, how can the agent, how much it can generalize over?
Well, it depends if you change the colors, the agent will adapt. The signature are defined so that any interaction allowing to detect the presence of the affordance will be captured by the signature. So you can combine multiple modalities, sensory modalities. So yes, the signature can handle any property that allow to detect the presence of the affordance.
Thank you. Another question over there?
Thanks for the talk. I'm not sure. Could you detail a bit more how is implemented the visual attention? Is it through the weights of rewards and costs, or what you showed, attraction, repulsion, and or is there any specific mechanism for the visual attention?
There's not visual attention. In fact, which part are you referring?
I think so. I haven't understood that part. So
in fact, when you perform the projection of the signature, you can scan your environment and detect here the sequence allowing to move toward an affordance. So by doing this, you can define a form of representation of the space through sequence of interactions. Then you have after the space memory, that is a complex model that can handle the whole space, including the space behind the agent, to define the data structure. I don't remember if I show some of them. Yeah, for example, yeah. So this is content of the space memory. Space memory define the affordance through triplets. So you have the affording interaction, an interaction that allows to move toward this interaction, and the distance in terms of minimum number of interaction allowing to reach this affordance. So the agent represents the context with this kind of triplets.
Thank you, Jamont. Let's salute our speaker.